Okay, so example 20.4. You can see that some of this is crossed out. The AP exam this year is not going to be testing you on Unit 8, which includes the pH. So this problem originally asked us to solve for pH at the very end. That's going to be assuming that you've completed Chapter 19, and we haven't and we won't for the AP exam. Okay, the solubility product constant for magnesium hydroxide, okay, MgOH2 is this value. Calculate the molar solubility of magnesium hydroxide. So go ahead and pause the video, try this on your own, and let's see if you get the right answer. Okay, as always, we're going to write a valid reaction. So Mg OH2, and it auto-corrected for me. How convenient. Mg2 plus 2 OH minuses. Okay, KSP is given, wants us to work backwards. Okay, so just like we did in the previous, we can assume we're trying to find this value. Our Mg2 plus and our 2 OH ions are going to be respective or relative to that value. So now because there's a coefficient, then whatever dissolves is going to be 2x. Okay, so KSP, we can write our expression. This one is raised to the power of 2, remember that. Let's plug our values in, and this is going to be given, give us a certain value. Okay, so Mg2 plus is x, OH minus is 2x raised to the power of 2, and that's going to equal the KSP value of 1.5 times 10 to the negative 11. And once again, that was given in the problem. So you can stop and go ahead and solve. Okay, when you simplify this, this gives me 4x to the third. Okay, equals 1.5 times 10 to the negative 11. When you solve for x here, I'm not going to do the algebra, you end up getting 1.6 times 10 to the negative 4 molar. That is the molar solubility. That's how many moles per liter it does dissolve. Now, I'm going to read a little bit further on, okay, before we go to the next video, and highlight a few things. Now, this is an excerpt from Chapter 19.1, the common ion effect in buffer solutions. Okay, you must be able to identify, and this is what will be tested, you must be able to identify the solubility of a salt and or the value of KSP for the salt, which we've just learned how to do. Okay, based on the concentration of, now this is a new part, a common ion already present in solution. The solubility of a salt is reduced, okay, and you'll want to kind of highlight this and kind of remember this. The solubility of a salt is reduced when it is dissolved into a solution that already contains one of the ions present. Okay. The impact of the common ion effect can be understood qualitatively using the Chatelier's principle, okay, or calculated from the KSP of the dissolution process. If a solution is made in which the same ion is produced by two different compounds, the common ion, okay, effect is exhibited. Buffer solutions are solutions that resist change in pH. When acids or bases are added to them, buffering is due to the common ion effect. Okay, now, luckily for you guys won't have to do these crazy calculations for acids and bases, but keep in mind you might hear that word buffering or common ion come up. Okay, so there are two common kinds of buffer solutions, and once again, your AP test won't test you over acids and bases, so this is more of just enrichment material right now. Okay, so there are two common kinds of buffer solutions, solutions made from a weak acid plus a soluble ionic salt of the weak acid, or a solution made from a weak base plus a soluble ionic salt of the weak base. Now, if several salts are present in a system, they all ionize in the solution. If the salts contain a common cation or anion, remember that's a positive and negative ion, these salts contribute to the concentration of the common ion. Okay. Contributions from all salts must be included in the calculation of concentrations of the common ion. So basically all we're saying is you're going to factor in and add in those concentrations. The solubility product expression tells us that the equilibrium concentrations of the cation and the anion are inversely related. That is, as the concentration of the anion increases, the maximum concentration of the cation needed for precipitation to occur decreases. Okay, now precipitation, remember that is in solution. Okay, when the substances are in solution, meaning in the aqueous form, they precipitate out to that solid form. Okay. Now, consequently, the solubility of an ionic compound depends on the concentrations of other salts that contain the same ions. Adding a common cation or anion shifts a solubility equilibrium in the direction predicted by Le Chatelier's principle. As a result, the solubility of any sparingly soluble salt is almost always decreased by the presence of a soluble salt that contains a common ion. Now we're going to do example 20.5 on the next video. After you see this,